Audio Jungle. Audio Jungle.
Rocket, right? So as we know that if you go for the propulsion system, so or propulsion engine, so we have two types: air breathing engine and non air breathing engine. Okay, that propulsion engine, we have a two types. It is nothing but air breathing engine and non air breathing engine. In this air breathing engine, we have seen that types of engine. It was basically a constant volume engine, and constant pressure engine. Here if you check, these are the IC engine and Wankel engine. What are the constant pressure? Constant pressure engine are ramjet, okay, turbojet, turbofan, turboprop or turboshaft. All are the constant pressure engine. What about non-air breathing? So this non-air breathing engine, our focus is what now? This one is what totally done. This is what jet propulsion. This is jet propulsion part, okay? In non-air breathing engine, this is basically rocket propulsion. Here also we have a non-air breathing, we have a three types. That background you should know, okay? Without knowing anything, if you go, then it is not fine actually. The basic thing you should know, then. So this non-air breathing, we have a engine, we have a photons engine, might you heard or you have submitted your mini project or something, photons engine, okay? Then rockets engine, photons, rockets engine and solar cell, okay? In this rocket, again we have a two types. This rocket we have a two types, and these are nothing but chemical and this one is non-chemical. Okay, this chemical, again we have three types. This chemical, again we have three types. What are that? These are solid, liquid, hybrid. And non-chemical, 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 these are electric, okay, nuclear, and solar. Okay, just listen carefully this explanation. Propulsion engine, two types we have: air breathing and non air breathing engine. Air breathing constant volume engines and constant pressure engines. In constant volume engine, IC engine, okay, internal combustion like steam engine and all. And Wankel engine, constant pressure engine, all jet propulsion engines what I have taught previously. It was turbojet, turbofan, turboprop, turboshaft, ramjet. These are the constant pressure engines. So this part is what done. Okay, now coming to non-air breathing engine, we have three types basically: photons, rockets, and solar cell. Okay, in this photons, rockets, and solar cell, rocket engine if you talk, then again they have two types: chemical and non-chemical. Chemical rocket engine have three types: solid, liquid, and hybrid. Hybrid, as the word you can understand, hybrid means combination of solid and liquid. And non-chemical engine, it is the part of rocket non-chemical engines are electric, nuclear. You This is very practical word. You have heard this many times, like electric rockets engine, nuclear rockets engine, solar rockets engine. Yes or no? So these are the rockets engine but non-chemical. And solid propellant rocket engine, liquid propellant rocket engine, hybrid propellant rocket engine. This word also you have heard many times. So this is the rocket engine, but type is chemical types, and non-chemical, electric, nuclear, and solar. So this, differentiation and all the classification you should know at least. So where is our focus? Our focus is here only. See, this is our focus. Our focus is what? Here only: solid, liquid, and hybrid propellant engine. This is our gate syllabus here. Earlier, this was the syllabus, ramjet, turbojet, turbofan. So similarly here, so our focus is what? On solid, liquid, and hybrid. All right, remember this. Fine. So now we can say this rocket propulsion, what we are going to study here. This is the rocket. A rocket is a propulsive device that produces a thrust force, on a vehicle by injecting mass a high relative velocity. High relative velocity. This is what rocket propulsion. Now, if you check that very minor difference between the jet propulsion and rocket propulsion. First, you have seen it is air breathing and non-air breathing. That is okay, but Another minor difference in rocket propulsion is basically the rocket propulsion system, they are carrying both. In jet propulsion, they are taking air from the atmosphere and ejecting gases through the nozzle into the atmosphere. Okay, that is the one thing. Second thing, for rocket propulsion, they are not taking air from the atmosphere. That's the reason it is called non-air breathing. Non-air breathing. Okay, so they are not taking air from the atmosphere, they are carrying. So the reason why, the reason is simple. Once you are going for the space mission, that time your rocket propulsion system will be useful, you can say. Actually, this atmosphere is what, like your jet propulsion, like all the engines, turbojet, turbofan, I told you that day, it is flying in stratosphere, and stratosphere altitude from the sea level is only 11 kilometer. Hardly it will go fighter aircraft, if it is, then hardly it will go to 25 or 30,000 feet or 35,000 feet max to max. Not more than that. So this is the atmosphere only. Okay. So here in atmosphere, air breathing system or air breathing engines comes into picture. Okay, but above this 35,000 feet, if you go, then the density of the air is what reducing. You have seen that atmosphere chapter, pressure and temperature and density variation you have seen. Okay, so the temperature is what initially it is decreasing, then constant in stratosphere, then again increasing, but pressure and density is what continuously decreasing. Once you go in, you gain the altitude, then pressure and density will be continuously decreasing. So at some level, some particular altitude, density is what air is what not available. Now you know that it is space now. So in space there is no air. So that's the reason rocket propulsion system will be non-air breathing system, and it will be useful for the space mission. Okay. Jet propulsion, it is for the commercial, for the fighter aircraft, commercial aircraft, passenger aircraft, and it is in atmosphere. Hope you understood that difference. I'm not going in that so much detail, but it is very clear now. Okay, so these are the minor difference between rocket and propulsion and jet propulsion. Rocket propulsion useful for the space mission, but jet propulsion only for the atmospheric mission only, like passenger or commercial fighter, that one. All right, now, so this difference is what now clear. What are the another major difference? So in air breathing engine, that I told you, it uses atmospheric air for the combustion, because it is air breathing and obviously it is flying in atmosphere, so air is what available. But what about rocket engine? That rocket engine will carry its own oxidizer and fuel, because in space there is no air. No? So it will carry. So rocket engine always carry both oxidizer and fuel. Air breathing engine, jet propulsion, carrying fuel, that is okay, but air it is taking from atmosphere and exiting to the atmosphere. No? It is not carrying air breathing engine, but rocket engine carrying the air, and that air is called oxidizer. Okay, called oxidizer. So based on this oxidizer and fuel, what rocket engine is what carrying, based on this we have a type of rocket engine: solid propellant, liquid propellant. What is the propellant? I will tell you. Second difference between the air breathing engine and rocket engine is, obviously air breathing engine cannot operate in space in vacuum, but rocket engine can operate in atmosphere as well as in space, because it is carrying its own air oxidizer, so it can operate in atmosphere as well as space. That air breathing engine, like all turbojet, turbofan, its performance is dependent on altitude and flight speed. Okay, but that rocket engine, its performance does not depend on altitude and flight speed. Why it is depending on altitude, air breathing engine? Because of the density variation. I told you, because density is what decreasing, so mass flow rate will be decreasing, and mass flow rate is what decreasing, so obviously thrust will be decreasing, many things, changes will come into picture. Okay, temperature variation, because of that also, that performance of the engine will be changing. But in case of rocket engine, that performance does not depend on altitude or any flight speed. Okay, that air breathing engine cannot operate beyond supersonic speed. Let us say for turbojet Mach number 5, more than 5 Mach number, it is for even turbojet, that performance will be decreasing. So in simple word, we can say that air breathing engine cannot operate beyond supersonic speed Mach approximate 5, but that rocket engine, it can operate from 0 to 25 till 25 Mach number, it can operate rocket engine. Okay, it is very nominal 10-15 Mach number for the rocket engine, but maximum Mach number possible for the jet engine or air breathing engine is 5. Okay, for the air breathing engine, that rate of climb decreases with altitude. Okay, but in case of the rocket engine, rate of climb increases with the altitude. Okay, so these are the basic difference, and many more you can analyze, you will get that, but these are the major difference between the air breathing engine and rocket engine. All right, now so if you go for the types of that chemical rocket engine, because I said here, this is our focus check, this is our focus chemical rocket engine, where solid, liquid and hybrid. So this is our concentration now. So among all, I will take these three types of rocket, and we'll say the types of chemical rocket engines. So basically, chemical rocket engine. So here, this is nothing but solid propellant, liquid propellant, and hybrid propellant. Okay, so in short, propellant rocket, no? Similarly, liquid propellant rocket and hybrid propellant rocket engine. Okay, engine. So this is called, in short, I will write everywhere SPRE, solid propellant rocket engine. LP, in short, everywhere I will write. So please remember this: liquid propellant rocket engine, hybrid propellant rocket engine. Okay, HPRE. Chemical rocket engine, we have a three types: solid propellant rocket engine, liquid propellant rocket engine, and hybrid propellant rocket engine. So if you go for the solid propellant rocket engine first, so solid propellant are basically both fuel and oxidizer are contained in same casing or combustion chamber. We do not have separate uh, vessel for the oxidizer and fuel. Why? Because it is solid propellant. So in solid propellant, what will have both fuel and oxidizer will be containing in same casing. Okay, what is the casing and all, I will tell you. And the propellant charge, okay, the propellant charge is called grain. So you might have seen in your college lab and all that propellant. So that it is a solid form, okay, and that propellant charge is called grain, okay, and it contains the entire chemical ingredients for complete burning. Okay, so if I draw the diagram, so the diagram will be like this only. SPRE, number one, SPRE, solid propellant rocket engine. So need to draw this diagram. Okay, now we have here okay. So basically is called this is called grain. I told you that propellant charge. So this is called grain. This is called casing. Okay, casing, outsider, and here this is called liner. Somewhere here this is igniter, will ignite the propellant. Sorry, let's correct this. Here, this is what igniter, and what is this? This is nothing but payload. Payload means it can be anything. If it is missile, then it is warhead. Okay. Otherwise, for the space mission, we have a satellite and all. So it will be payload. So for the SPRE, solid propellant rocket, so this is what solid propellant. And especially this part is called grain. You have seen my in your industrial unit or somewhere you might have seen or in your college lab. So this is the solid propellant. Okay, this is the propellant solid form. Both part available here. Oxidizer plus fuel okay, and it is in solid form. This is what nozzle. Fine. So this is the SPRE, solid propellant rocket. It is available in single casing only. Okay. So as I told you that this once here, this is the igniter, and igniter will ignite once, then combustion will start. Okay, and once combustion will start, then definitely whatever the exhaust gases are available, that exhaust gases will move in this way. and it will come like this. Anyway, so if you check the advantages for the SPRE, so it is very simple to design, okay, and very easy to handle and store, unlike liquid propellant. Why storing is very easy? Because we are not having extra vessel, because if it is liquid form then we should keep separate vessel, but it is in solid form, so we have mixed oxidizer and fuel ingredient, we have mixed and we made in solid format, so definitely separate combustion uh, like vessels not required. So it is very a good thing for this solid propellant. Okay, so storing is very easy. Better reliability than liquid propellant. Obviously you have to compare with another like liquid propellant, so reliability is what good for the solid propellant compared to liquid propellant. And it is very easy once you go for the multi-staging rocket system. So in multi-staging rocket system, if you are going, then this solid propellant rocket system is what easy to use for multi-staging. Okay, and these are the advantages. Okay, so no need to write here, so just listen and remember it. Okay, what is the biggest disadvantage of this? The disadvantage of this is what lower specific impulse. In fact, if you compare with the liquid propellant rocket engines, then both liquid propellant and hybrid propellant rocket engine, LPRE and HPRE, compare with this, then this SPRE, this solid propellant rocket, will have a lower specific impulse. And again, one more difficulty for this disadvantage is what to turn off. Suppose combustion you have started, okay, thrust is required, then combustion is started. Once you have ignited, then that combustion will be continuous. I mean, the burning of this propellant will be continuous. You cannot stop that. But in case of liquid propellant rocket engines, it is very easy to stop. How? Because they are having separate vessels and it is in liquid form. So you will have a, like, tap system, so you just close that, so that liquid will not come out, so, or liquid will not mix in mixer, then definitely combustion will stop. But here it is solid SPRE in solid propellant rocket engines. Once combustion is started, once burning is started, it is very difficult to turn off. Okay, so these are the uh, disadvantages. Now, similarly, we'll go for the liquid propellant. So, how liquid propellant uh, rocket engine will have? So, I will show the diagrams. It will be easy to understand. Second is LPRE. So, I will draw the diagram, and with the diagram, you need to imagine like how it is and how it is working. So, same thing. Just you have seen the HPRE. We have a the liquid system. So, what you will have? So obviously it will be bulky compared to that solid propellant. Why? Because it is having the separate vessels, and these vessels are like this. check. We have a separate tank. And here somewhere okay. So that fluid will come like this and it will mix here. So this is what oxidizer. This is the OX, I can say oxidizer tank. And this is what fuel. Fuel tank. Okay. This is what pump, because it is the liquid, so pressure required to take fluid from the vessel or tank. How you will get fuel out from the tank? You have to apply pressure. That suction pump will be there, and that suction pump will used to take fluid from tank to combustion chamber. And here we have a combustion chamber. This is the combustor. And now this is the payload. Okay. And this is the exhaust gases coming out. Okay. So basically this is what nozzle. So two tanks required. One is what fuel tank, another is what oxidizer tank, and all both are in liquid format. The liquid will be taken from the tank to the combustion chamber with the help of pump. Suction pump will be there. So see, two tanks required, two suction pumps required, sometimes regulator also required, okay, or gas generator required. So it is very bulky, very spacey, more space it is taking compared to the solid propellant rocket. That's the reason most of time we are seeing that solid propellant rocket engines. Anyway, so these are the components available. I have drawn this diagram so you can understand in this way. And that fuel and oxygen, that is oxidizer, you will take from the oxidizer tank and fuel tank. You will take and you will mix in combustion chamber. So in this combustion chamber we have mixing, and it is very volatile. Okay, so here it is mixing and it is burning. Okay. So this is the system. Hope you understood this. This is what LPRE, liquid propellant rocket engine. So obviously compared to that solid propellant rocket engines, this will have some advantage, and obviously there will be disadvantages also. So LPRE are stored in separate tank. Here you have seen fuel tank and oxidizer tank. It is preferred for a large spacecraft and ballistic missile. However, the design of an LPRE is quite complex. I told you because of this component, two tanks, two pumps required. Okay, so LPRE is quite complex and requires specialized nozzles also, because in the nozzle we should have a proper mixing as well as combustion also, because whatever the combustion occurring, it is in combustion chamber, but it is connected with the nozzle directly, no? So that design should be proper. So what are the best thing for the this liquid propellants are? Number one, LPRE can be reused. I told you in case of the SPRE, solid propellant rocket, once burning start, then you cannot stop that. But LPRE you can on and off. You can start and you can stop with the help of the pump, or you can use knob somewhere. No? Here you can use knob also here, so you can on and up. See, this is the knob. You rotate it, so on off system will be there. So this is the one very important advantage. LPRE can be reused. Okay. It provides greater control over thrust. Obviously, you can reuse, and at the same time that what amount of fuel and what amount of oxidizer, if you increase or decrease, based on that you can control the thrust also. Number three, it will have a higher values of specific impulse. Okay, so a specific impulse compared to SPRE, this LPRE is having more specific impulse. Just like in case of the jet engine, you have seen a specific thrust. In rocket, we have to talk specific impulse. I will give the formula. Okay, so these are the few points, advantages. It can be used for a long duration application also, because it depends on the amount of the fuel and oxidizer. You can store more and more. You can use for the long time. Okay. Disadvantage is engine is quite complex compared to SPRE, obviously, and very bulky compared to SPRE. It becomes, because of it becomes heavy. Okay, and complicated design also. Now we'll go for the hybrid propellant rocket engine. That diagram I will show you, no? So easily you can understand. Third is nothing but hybrid, HPRE, hybrid propellant rocket engine. Okay, here if you go for the design, so payload. Okay, you will have a the both solid propellant and liquid propellant. So this is the solid propellant. Okay, and we have here, this is the liquid oxidizer. This is the pressurized gas, and this is connected to the tank of liquid oxidizer, LOX, liquid oxygen, basically it's oxidizer, and it will be supplied to this. Even though we have a wall also, this is the wall, This is what injector, and it will spray. This is what solid fuel. This is the LOX liquid oxygen oxidizer. Now this is connected with the done. So both thing here you have that solid and liquid both, so hence it is called uh, hybrid. Okay, so hybrid propellant. Now in order to achieve better performance, elements from HPRE and LPRE, because you have seen for HPRE there is some advantage, so at the same time some disadvantages also there. Similarly, for the LPRE liquid propellant rocket engine, there are some advantages, but at the same time some disadvantages also there. So you have combined both, and you for the better performance, and you got new engine called HPRE, hybrid propellant rocket engines. So in this we are using both solid and liquid types of the propellant. Okay, so the best outcome you may have. Similarly, liquid propellant, just like a liquid propellant rocket engine, this HPRE also can be reused because we have a controlling system here. Provides greater control over thrust. In solid propellant, you had seen there was no control over thrust, but in liquid propellant and in HPRE both, we have a greater control over thrust. Okay. It has a start, stop, restart capability, just like LPRE, liquid propellant. Okay, and compared to LPRE, it has relatively lower system cost because we have reduced number of pump, gas generator, we have reduced number of vessel also at the same time. So it can have higher values of average specific impulse compared to HPRE. So these are the advantages, and disadvantages also available for this. Like this engine is quite complex compared to LPRE, and it has lower density of specific impulse compared to HPRE. So these are few disadvantages. Okay, becomes heavy, particularly for short range application. It takes much longer to design and develop. So these are the few points which is not like you can say it is disadvantages. Okay, but if you combine this, so both advantages of SPRE and advantages of LPRE you can combine, and finally will get better performance of the rocket system. So hope you understood. These are the ideas. You already have gone through this in your coursework in detail, advantages and disadvantages. So for competition point of view, I'm not going each and every point of the theories point of view. I'm not going, but I have shown you the diagram, and at least you can differentiate. Okay, you can recall that, that, but you now you can recall fine. For SPRE, there is only solid propellant system in liquid. These are the things how it works. So that mechanism at least you got. But I will tell you, in your gate problems, they are not asking advantages, disadvantages, but yes, comparison they are asking between a specific impulse. So one table I will give to you, and for all type of engine, engine, nuclear rocket, solar rocket, okay, and solid propellant rocket engine, liquid propellant rocket engine, hybrid, for every types of the engine, in fact jet engine, and also specific impulse I will give one table. That theory they are asking. Okay, rest they are not asking that theory, design point of view or component point of view, they are not asking, only numerical they are asking. So based on your gate syllabus I am going. Okay, Fine. Now we'll have a thrust equation for rocket engine. So from here, this is your gate syllabus. Okay, so focus. Thrust equation of rocket engine. So here, if you go the basic one, for this basic jet engine, this was the V infinity and mass flow rate was m dot a. This is the combustion chamber. So you have burned here fuel. This is compressor. This is turbine. This is the combustion chamber. And here exit, you had seen it was m dot a plus m dot f, and v exit was the exit velocity. V exit, and exit pressure was PA. Here atmospheric pressure was P infinity. So what was the thrust for this jet engine? You had written m dot a plus m dot f VE minus m dot a V infinity exit area is what A. Yes or no? This was the thrust. This is what jet. Okay. Now going to the rocket engine. This is the rocket engine. So now definitely here we have this propellant system and all. I am just drawing solid one only. So we have a exit velocity and exit pressure also. Exit area is A, and here obviously atmospheric pressure is P infinity. But it is non-air breathing, so V infinity will be 0. So it is flying with the exit velocity, not V infinity. So now for this, if you write thrust equation, so because it's a non air breathing, so first of all you can say V infinity will be 0 for this. Just listen carefully. You can say m dot, because non-air breathing, so m dot a will be 0. Yes or no? Non-air breathing. Non-air breathing. So what will be the thrust equation? Thrust is nothing but m dot a plus m dot f. So instead of this m dot a plus m dot f, we have to write this combined one. This combined one we have called m dot P, mass flow rate of the propellant, okay, into exit velocity plus PE minus P infinity into A. Okay, P minus P infinity into Okay, fine. So what is the thrust? So I have compared this, and finally I got thrust equation is nothing but m dot p into ve plus pe minus p infinity into ae. No need to derive, just I have compared from there, and I have written this thrust equation. You can say T is equal to now m dot p ve plus pe. P infinity you can write atmospheric better into ae. This is the thrust equation of the rocket. Okay, now T is thrust, m dot p is the mass flow rate of propellant. If I said mass flow rate of propellant, then both liquid and both oxygen and fuel both are coming here. Okay, m dot p. ve is called velocity component at exit of nozzle. Okay, rest P is pressure exit area at exit of nozzle. Okay, and PA is the atmospheric pressure. Okay, PA is the atmospheric pressure or ambient pressure. What is the PA? Ambient pressure. This is the thrust equation. But now, what about space? Because you said this rocket system is what working in space. So definitely in space there is vacuum. So what is the atmospheric pressure? So I can write in space PA will be 0. Alright, so now what is the thrust? This thrust is nothing but m dot p into ve plus pe into ae. In space, okay, or you can write in vacuum of the space. So the PA will be 0. Alright. For given design, the nozzle value of exit pressure PE is fixed. They are not going to change because combustion and all whatever it is starting, it is not depending on the surrounding. So design of the nozzle, for given design of the nozzle, the value of exit pressure PE is fixed. So during flight through the atmosphere, the ambient pressure PA decreases continuously. Yes or no? If it is in atmosphere, so PA is what continuously decreasing. So as the result, the thrust increases with the altitude. How? You just write the formula, then you will understand what is the thrust actual formula. M dot P VE plus PE minus PA. This was the formula. Relate now. Altitude increases means PA decreases. Once PA decreases, once PA decreases, thrust increases. Altitude decreases, PA increases, and then thrust decreases. You remember it, okay? I'm talking about in atmosphere. It is in atmosphere. This is in space. Okay. If you draw the plot, how it comes? I can draw here only. This is the thrust. This is the altitude. Altitude. Okay. This altitude is what in kilometer. So I can use a separate number. Once altitude increases, thrust increases. Now see this graph. This is for 1 marks objective. You need to remember. Once altitude increases, check. PA decreases, so thrust increases. So this thrust will be increasing. So you can say from here, this thrust is what increasing like this. Why? Because altitude is what increasing, so thrust is what increasing. It will be increasing like this. But at some altitude, PA becomes zero. Space you will achieve. Once PA achieved, then thrust will be constant. Like this. So here this is what thrust constant here. Thrust increases with altitude. At this particular altitude here. At this particular altitude, PA becomes 0. PA becomes 0. Once PA becomes 0, then thrust will be constant. You need to remember for 1 marks, okay? Right. Condition for maximum thrust. If you check the formula, the standard formula of the thrust for rocket, so it is nothing but T is equal to m dot P into VE plus PE minus PA into PE. So as you know, m dot p is what constant. Okay, m dot p is constant, and that exit velocity totally depends on the combustion chamber property. So that you can say VE is also constant, m dot p mass of propellant it is also constant, mass flow rate of propellant it is also constant. What is the variable? Variable is only this pressure term. So we can say for maximum just differentiate with respect to area. So what we will have? It will have a dt by dA. So you will have PE minus PA only, and for maximum it will be 0. This is the condition for maximum. No? So what is the result you got? PE is equal to PA. When PE is equal to PA, then thrust will be maximum. Make a note of it. Okay. When exit pressure becomes atmospheric pressure. When exit pressure becomes atmospheric pressure, then we will have a maximum thrust. And this condition is called as, if you remember, optimum expansion of nozzle. I had explained this. So when we get maximum thrust in rocket engine? When there is the optimum expansion in nozzle. Optimum expansion in nozzle. Let me write there. Okay. And this will be for the given condition in combustion chamber. I told you this thing will happen when the combustion chamber condition is what given and it is fixed for that. Once that combustion chamber pressure and temperature will change, this criteria will also change. Okay. So what is the value of maximum thrust? I can write T max. So T max is nothing but m dot p into VE now. Why? Because P is equal to PA. So pressure thrust will be 0. So this value always remember. Okay. You need to remember this. This is very important. So the condition provides a maximum thrust for a given chamber pressure and propellant mass flow rate. Okay, the rocket nozzle in which this condition is achieved known as optimal expansion ratio of the nozzle. So whatever this condition you have written here, PE is equal to PA, or whenever you are getting maximum thrust, it is for a given chamber pressure and temperature and propellant mass flow rate. Always remember, if that value will be changing, then this condition will be same. PE is equal to PA, that will be same, but that magnitude of these values will be changing because PE will be changing that time. When the combustion chamber pressure and temperature will be changing, then exit pressure definitely it will be changing. Okay, right. So I mean, at which altitude maximum thrust you will achieve, it will change as per the value changing in combustion chamber. Understood? Fine. Now, all right.